Hello, my name is Steve Miller, and this is recordings and notes on the Navier-Stokes equations, the greatest and most important set of equations ever devised. This class is organized in parts and will grow over time. Right now, I'm going to go through the class mostly in a linear fashion as it was taught during COVID. In this particular class, it's mainly introduction and overview of the material. I'll tell you a little bit about myself. We'll skip the syllabus because that was for the class when I was taught at University of Florida in the Department of Mechanical and Aerospace Engineering, joint with mathematics. We'll talk about the motivation of the class and why we study it. Then we'll look at a course outline, the class outline, and that could be modified later, but it'll be the initial outline. I'll also talk about the source material, which includes books and journal articles over time, from the time of Navier and Stokes and before, all the way up through today in the 2020s. And we'll also talk about just examples of turbulence and why do we care. And we'll talk about particular numerical integrations and looking at discrete solutions of fluid dynamics and turbulence through computational fluid dynamics. But this class does not necessarily focus on turbulence, transition, or laminar flow. It's focused on the equations themselves, the physics of flow, and their predictions. A little bit about myself. It's a bit dated, this slide, but in 2024, the current DARPA Director's Fellow, Defense Advanced Research Project Agency Director's Fellow in the United States of America, for those non-Americans. DARPA is an interesting agency and it's worth reading about online. I'm currently at the University of Florida Mechanical and Aerospace Engineering, but you never know where you're going to end up in life. I used to be at NASA Langley as a research aerospace engineer and was a full-time civil servant from 2009 to 2016. I received my Ph.D. at Penn State in aerospace engineering under Professor Philip J. Morris, master's at the same institution, studied mechanical engineering with a bachelor's at Michigan State, briefly studied in Taganrog State University in the Russian Federation, and did some early studies at Eastern Michigan University in Eastern Michigan in Ypsilanti, near where I grew up, in Detroit and Ann Arbor. And I spent my early life in Michigan. You can find more about me online, I'm sure, if you want. And of course, you can contact me through email and other means, webs, LinkedIn. I don't have much social media, and be careful. There are people who have impersonated me online, so I apologize. I run a research group, and it's called the Theoretical Fluid Dynamics and Turbulence Group. And generally, as a group, we are interested mostly in understanding the physics of turbulence mathematically and physically. In particular, the goal of my career is to understand fluid dynamics and turbulent flow in particular mathematically and physically. I personally think this is probably an impossible task, and many people have undertaken such a goal for their life goal. But I think you have to be realistic that so many people smarter than me have studied this subject and have never achieved even a fraction of physical and mathematical understanding of fluid dynamics, let alone the Navier-Stokes equations. Also, my group is interested in understanding how sound is produced and propagated through turbulent fields. So that means that turbulence itself and a fluid creates waves, noise or acoustic waves, and we're also interested in understanding the acoustic source and propagation from turbulent fields in fluids, which is liquids, gases, and plasmas. But this can be really, really difficult in itself. And since we don't understand turbulence, I don't think it's very much possible right now to understand the physics of how turbulence produces sound. But oddly, we probably understand more about how sound is produced by turbulence than turbulence itself. Nonetheless, these are all central questions in the field of fluid dynamics and has been a subject of study for many years. And in these classes, I'll have some history, a lot of history, about people looking at turbulence and their interest in it. This class also talks about different ways to solve fluid dynamic problems, and I divide them in three categories. The first is analytical, the second is computational, and the third is experimental. And we'll talk in detail about what that means later. But my group mostly focuses on analytical or modeling and preference. And when we can't do that because of funding and grants, or maybe we're just not able to because we're not smart enough, we'll numerically integrate our problems away and do computational approaches, which is the field of computational fluid dynamics. So as I said, my own research is mostly on analytical type methods, or modeling flows and modeling noise. And people who enter the field usually get involved in computational work and combine it with modeling or get into experiments. I would think today most people are in the computational or numerical world, then experimental, and a few lucky people might be in analytical work today. So this class really focuses on the analytical and semi-empirical methods. That means analytical meaning just analysis and modeling using the Navier-Stokes equations, or semi-empirical methods which combines with empiricism, like combining data and fitting and modeling that way, or making reduced order or simplified models from the equations of motion. Also focuses very much on the physics of the flow, and we talk some about applications, but I'll probably do a lot of that verbally. Just for fun, I wanted to include a picture of my research group when I left NASA in 2016. This was located at the exit of the Hypersonic wind tunnel, and I brought my then students and collaborators to the tunnel, and I took their picture from the ground, and they're sitting in the exhaust ductwork, if you will, of the NASA 8-foot hypersonic tunnel. This is clearly larger than 8 feet, as you see, and that's because it's the exit. The 8-foot means it's the size of the test section, the cross-stream direction. The cross-stream direction is orthogonal to the main flow direction in the test chamber. That was a wonderful day, and it's one of my most favorite memories, so I always try and share this photo when I'm doing a class. So turbulence itself is, as Horace wrote, one of the last greatest challenges in classical physics, and that's even true today. If you go into the physics department, you'll see a lot of physicists doing work in particle physics, astrophysics, maybe gravity, and all kinds of exotic areas I don't personally understand. And today, people are still trying to understand turbulence, and people say, hey, this is still the last great area of classical physics that's not well understood. This is a picture of Sir Horace Lamb, Fellow of the Royal Society. And he was obviously a very, very intelligent person. He spent some time, I believe, in the University of Adelaide because he wasn't allowed to marry his wife in the United Kingdom at the time, so he went down and got higher-level professorships at University of Adelaide. If you visit there today, you'll see some buildings and places named after him. It's very beautiful. Once he obtained a higher position, he was able to go to, I believe, University of Cambridge. He wrote some amazing books, Hydrodynamics and the Dynamical Theory of Sound, and also a book on statics, which are just wonderful, and I highly recommend them. In a talk, an address to the Association of Advancement of Science in England, he wrote, "I'm an old man now, and when I die and go to heaven, there are 2 matters on which I hope for enlightenment. One is quantum entanglement, quantum electrodynamics, and the other is turbulent motion of fluids. And about the former, I am rather optimistic. I've met many people in my career who always talk about how difficult the field of turbulence is, and it's true, but it's almost like a religion, and I think it's dangerous to fall in that trap of the romanticism of the subject. And there's many other people who wrote similar quotes later on in life about turbulence, and you would recognize their names too. For example, Heisenberg might be another. Richard Feynman, they all have made similar jokes, but maybe they have replaced the thing they don't understand with their own, but kept turbulence as the thing that they might ask God about when they pass away. Throughout the class, I'll have sporadic biographies and tidbits, Here's one on Horace Lamb, who lived from 1849 to 1934, British. Applied mathematician, as I mentioned earlier. He was in Adelaide. And he wrote wonderful books like Hydrodynamics. I have a particular first edition from the NAACA that I had when they got rid of the NASA library at Langley. Dynamical Theory of Sound, Statics, they are well written and highly regarded even today. If you can find digital online copies or a used edition, I really recommend them. He was a student at Trinity College, and you might recognize some of these names like James Maxwell of electromagnetics and George Stokes, who carries the name Navier-Stokes equations. He's definitely known for different things in our field in CFD, such as Lamb waves. Not many people know his name as much today as some other people do. There's also a vorticity term, and he came up with the word, or is credited with the word, vorticity. Became a fellow of the Royal Society in 1884. There he is. Wonderful.